The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, we'll get started in just a minute. Wait for a few more people to jump on. Okay, let's get started. So today you're just going to go over the kind of basics of Inventor HSM, which is a plugin for Autodesk Inventor and part of the product design and manufacturing collection. So as a team, there's 5 of us on the manufacturing team, and we've got more than 50 years of experience across different facets of manufacturing, from data management, the CAD itself, but then also the direct manufacturing tool sets on the CAM side of things. And that's not just for Inventor, but also some of the fabrication products as well for building product suppliers. So the general workflow inside Inventor is once you've got the add-in installed, you have the CAM tab which appears on the ribbon, and a set of tools generally work from the left to the right on the ribbon. But you either open up CAD data that's been sent to you by a supplier, or you'd open up a file that's been modeled up by your design team, or you model something up yourself. So you open or create your CAD data as your first point. From there, then you need to define your job or your setup. And what that entails is telling the CAM system which object is the model, what your stock is, and if you've got any fixtures defined, what they are, but then also where your 000 coordinate system is, and the orientation of that. You can also specify some metadata in there for when you post out, so the program name and maybe a comment or a description that goes with that, and then which coordinate system you want to use at the machine. From there, you define all your operations, so typically facing, then remove all the material, do some detailing, and then some finishing, drilling, tapping, so on and so forth. Kind of rule number 1 with CAM is to simulate before you post. It's easy to simulate through the entire program. It's certainly easier to simulate through the entire program and catch a simple crash at that point, before just quickly reposting code and running it on the machine and regretting it later on. So yeah, number one rule in my book is always simulate, stock simulate before you post your code out. And then finally, convert your all the toolpaths on screen into G&M code that your machine will understand using a post processor. So it gives you a quick overview of the toolpaths that are available in Inventor HSM. You've got two groups on the milling side, 2D and 3D. Now, 2D and 3D is defined in Inventor HSM as either using inputs or edge inputs that you've selected, be that model edges or a sketch contour, versus using the model to generate the toolpath. So 3D toolpaths use the model, 2D toolpaths rely on your, as a user, the inputs you give it. So in this case here, you can see on screen that we've got a series of 2D toolpaths, and trace towards the middle of the screen here is actually a full 3-axis toolpath, so by some would be considered a 3D toolpath. And then further to the right, we've got thread, bore, circular. Again, they are toolpaths which are changing in continuously in all 3 axes, so it is a 3D output, but it's being driven by your selections, not the physical model itself. So it's generally quite simple geometry, which is being used as an input to drive the toolpath. This gives you a lot of control, but it also means that it's possible that you can gouge your model using the toolpath. So you have to pay attention, make sure that you've got your tool set to the correct side of the geometry, whereas that wouldn't happen with a 3D toolpath. So although this graphic doesn't show it, there is a 3D adaptive clearing toolpath and also a 3D pocket, which are roughing strategies, and 3D pockets a finishing strategy used to remove material based on the model itself, not the basic 2D inputs from the previous slide. But what we see here on screen are all the 3D finishing toolpaths that are available, and they're a mixture of, so you can see parallel is a step over strategy, whereas contour or ramp is a step down strategy. So contour and ramp are good in steep areas but bad in shallow, and parallel is good in shallow areas but poor in steep areas. So you have to mix and match the two. Most of the toolpaths on screen here will convert the model into an STL, which is a faceted mesh made up of triangles. And so that when you understand that and how that interacts with boundaries when you're doing your 3D surfacing, you'll see some noise which will appear in the toolpath in some situations, which is fine and is a standard feature of most CAM systems. But when you contrast that with a toolpath like Flow, that doesn't use an STL. It actually uses the wireframe with the underlying objects which construct the surface itself to generate the toolpath. So if you've got a really high quality surface, you'll get a really high quality toolpath, and there's no kind of linearization of the geometry from an arc to a series of lines like you'd get with an STL. Now, the downside to a toolpath like Flow is when you're creating fillets, for example, in your modeling environment, it's quite easy to end up with poor geometry, as the CAD system is trying to fudge geometry to create a valid fillet. And so in that scenario, when the CAM system extracts all of those underlying wires from the face, you can end up with converging toolpaths and that twist inside out, and you just get horrible results. So right tool for the job. Each toolpath has its place, and a lot of that comes with experience of just playing around with the toolpaths themselves, and then looking at some geometry and going, that particular toolpath is the one I need for that geometry, and yeah, that's just experience. All right, so we do have some multi-axis strategies as well. They're pretty basic, mainly for 5-axis. There's some limited simultaneous 4-axis but here you can see some options, and you can get quite creative with them. We won't be covering that today. And here's some the turn-in strategies, just in quick summary as well. And you can combine these turn-in strategies with the 2D and 3D milling strategies to create mill turn programs. But again, we won't be going over turn-in today. All right, so adaptive clearing is one of the kind of core features of HSM, and it's a constant engagement. It never over engages the tool in the stock when you're roughing and removing material. So the result is usually you can get a higher material removal rates in harder materials than you would with better tool life than you would have historically with traditional roughing techniques. So what is it? So on the left-hand side here, we've got traditional roughing, sort of like 3D pocket or 2D pocket as the equivalent toolpaths in HSM. And as the tool, you can see the pie section, the red pie section of the tool in the graphic. You can see it's coming along the bottom wall there. Is a nice, easy cut, maybe about 45% radial engagement. As soon as it gets into the corner, it over engages, and then as it goes into into a full slotting scenario, it's 100% engagement. So when you're setting your feeds and speeds, you have to set it up for the most loaded condition, which represents the smallest percentage of time that the tool's in that scenario relative to how it's cutting along the bottom horizontal edge there. So you've got a suboptimal result. And so what will traditionally happens then is you cut with a shallower depth of cut and a wider width of cut to overcome that, but you end up only using a small amount of the flute on your tool. Whereas the high efficiency roughing, adaptive clearing on the right, maintains that constant cutting angle and then works its way into the corner. So you can see that the kind of comparison of the two different toolpaths here as output within HSM. Now it looks like here we've got a lot more going on. The tool's traveling further distance than it is on the left-hand side, but on the left-hand side, typically you'd have to take that in a number of steps down in your Z-axis along the tool axis, whereas the roughing, the adaptive clearing, you can ramp, this is the red toolpath here, ramp all the way down to the bottom of the pocket and then cut at full depth. So we'll just do a quick animation comparison here. So in plastics and even in aluminium in some cases, this toolpath on the left is still quicker. And then on the right here, in harder materials, you're going to get much better run times. Now, a common mistake that people will make is they'll apply the same feeds and speeds that they've been using on traditional roughing toolpaths to adaptive clearing, and then when they get a longer run time because the tool's traveling a further distance, they then stop using adaptive clearing because they think it takes longer than the traditional method. But that's not a fair comparison, because often the case adaptive clearing can actually run at much higher feed rates than traditional roughing. So you can't use the same feeds and speeds. You have to use the right data, the right cutting conditions for adaptive clearing for it to be a fair comparison of runtime. All right, so just again, to kind of reinforce the fact that with traditional roughing, you're using just a small amount of your cutting flute. You're spiking the loads in the corners, and you're putting more load through your spindle than you need to. So it's not so good for your machine. Whereas you're getting a more balanced cut here with adaptive clearing and improving your tool life and also the life of your machine, and your spindle bearings are going to be happier and so on and so forth. All right, so getting started. There's a whole bunch of free learning resources available within HSM and within the community. So YouTube is obviously a really good starting point, and there's a couple of good channels for that. So if we have a look here, we'll go to just jump back there a second, from the CAM ribbon, the tab on the ribbon, you can come across the help and tutorials. You've obviously got your help file itself, and then some examples which are stored on your C drive, which you can open up and check out some of those toolpaths. This links you through to the HSM YouTube channel and then the discussion forums. So the help file, the tutorials here relate to the files in the examples folder that I just showed you in the help drop down, and there's also some additional tutorial files you can download from within here. And then there's a playlist here that the help drop down linked you straight through to, which gives you some more detail into what I'll be showing you today. And if you have a look at the HSM YouTube channel itself, there's a whole bunch of content on there. Now there's also the CAD Pro CAD CAM channel where I've created a number of videos over the years, and you can take a look at that. I don't post as often as I'd like to, but there are a few good little videos there for you to use as a reference. Then there's also in-product tutorials. So if we go back and have a look at the Get Started tab, there's from the CAD side, the learning path is really good, and then there's also the tutorial gallery. And if we have a look in there, we can search for all available tutorials. So these are, you can download them, right? So you've got some that are installed already, and then others which you can access and download. So if we have a look and search for HSM, we can see that there's 3 here, 1 for turning, some basic 2-axis. Now these are pretty cool because as you go through them, if you can't find a command, you can get the tool to highlight in the software where the command is that you need to use to get the job done. So these are well worth exploring if you're new to all of this. All right, so the user interface, we've already touched on the CAM ribbon. The CAM browser, once you've got it installed, you end up with an extra tab in the browser here. So you'll be used to, as an Inventor user, you'll be used to having model and iLogic, and then now you have CAM as well, which is available. There's the CAM options, so you may want to make some changes to the way some of the defaults, so that's available on the ribbon here. And my favorite one is to deselect combine operation dialog with CAM browser, which means that when you're editing toolpaths, you end up with a separate dialog like this instead of it being integrated into the browser. This feels more like Inventor to me, so that's how I like to have it set. So I can still see all of my toolpaths and access everything in my browser while I'm using this independent dialog to control how I want to program my part. Then, as we can see from the screenshots I've got on screen here, the dialogues are highly consistent. We've got milling and turning toolpaths on screen, as well as full 5-axis and basic drilling or hole making toolpaths, and they've all got 4 or 5 tabs, and each tab has the same content in it over and over again. Also, you'll see that in the adaptive, as an example at the top here in the top left, on the passes tab we've got blue lines, and then on the linking tab we've got green and yellow lines. Now they match the colors of the toolpath elements that you see on screen. So when you see something you want to change, you can immediately associate that with the tab and go to the tab and find the setting to make the change that you need. So the learning curve, this helps smooth out the learning curve quite dramatically, and it's pretty unique for HSM compared to competitive products. Right, so let's get into doing some setup, actually doing some programming. All right, so you can program in either the part environment inside Inventor or in the assembly environment. Now, I've got an assembly open here, and by having an assembly open, I can include my my work holding as templates. So I can have a library of all of my fixtures and vices and clamps set up and bring those in and plan out how I'm going to actually manufacture the product, each setup, plan out the work holding, create drawings of it if I need to communicate that with a setup guy or machinist. Now here we can see that I've got, I could set up limits on here as well. which I haven't done here, but we can see that I've got my sliding jaw and this is a fixed jaw. So if I want to now insert my second operation, I can do that. I've got a sub-assembly here with my part and second operation stock set up. I can bring that in, and we can set up the constraints that are required and create another one between these two. Okay, that's fine. And we'll just create a joint between this edge here and this, and it will just need to get the orientation right. Flip that way, and now it just pulls the jaws into place. So it's pretty straightforward to get your job into your fixtures and work holding once you've got your templates set up. Now, just to show you, if I open up this part, I can create setups and toolpaths in this environment as well. And I just have a cam tab which appears within the part file if need be. So often if it's something quick and simple, then you can just program straight within the part environment. All right, so let's do our first setup. We're going to do the first side. And the first question that you're asked in the setup tab is whether what type of operation are you doing. So are you milling, turning, cutting? So this is plasma, laser, water jet, or mill turn. In this case, I'm milling, and depending on what you select in here, it will change the options which appear in this dialog. Okay, so it's important that you get that right. And I'm going to set up my coordinate system. So I want to set you can see here that the Z is currently pointing in the wrong direction. It needs to point up towards my spindle. And I can just pick a face and my Z axis will become normal to that face. And at the moment, my origin, my 000 position is set up to my model origin. Now I need that to be elsewhere. So we'll just go with stock box point at the moment. And I need to specify my model. And now you can see that my stock, this yellow bounding box, has shrunk to shrink wrap around my model. Now I can set up my fixtures. Now this doesn't stop the toolpaths from generating where there are fixtures, but what it does do is it adds the fixture to your stock simulation, so that if your tool or holder crashes into your fixture, then it will show up as a collision in simulation. Now, on the stock tab here, there's a bunch of different options. You can use this kind of graphic based stock, and you've got all these different options here. So you can go fixed size, relative size. These are as boxes or cylindrical stock, or tubes, or from solid. Now, I like to use from solid. And I'll show you why. So if we come back to the model tab here, I'm just going to turn on my stock, both stocks. I've got my first operation stock and my second operation stock in the same position, because I've planned out what my second operation stock's going to look like, and I'm effectively going to be machining to that rather than the model itself, in theory. Okay, so if we come back to our cam setup here now and edit this and change my mode, my stock mode, to from solid, and I can now pick my op1 stock. And that's it. All right, so let's get our first toolpath underway. I'll just make sure that I've got, oops, here we go. Got everything set up there. So we're going to create our first tool to rough this job out. So from the tool library up here, just quickly give you an overview of this. You've got these folders on the left hand side, and at the moment I've got 2 documents open, and so they appear in here, and I can see that on this prismatic component I don't have any tools, but in this main CAM assembly I have all the tools that I've used to program these 2 setups here. Then I've got my libraries and sample libraries. Now you can have these libraries stored on a network drive or in Dropbox or something like that and synced with other colleagues, and you can create a new library and pick where that is on your drive. Now you can organize these by machine or have one library covering all your tools, or libraries per material, however you want to manage it. But typically you'd create new tools within this library, and then when you want to use a tool in a toolpath, you go to the library, select the tool from your library, and it will copy that tool across into your document. Once that's happened, the link between the tool in your document and the tool in your library is completely broken, which is a good thing, because, for instance, you may want to adjust the stick out of your tool from one job to the next. So you always want to try and keep the stick out of your tool to a minimum to minimize chatter. So that's the kind of thing that you would adjust from one job to the next. Now, once we've got our document or our library selected, so if we, in this case, we're going to go to my new library and create a new milling tool, and we'll go with a bullnose tool that's 12 mils, and we'll put a 1.5 mil corner radius on it, and we'll leave everything else as default. Now on the general tab here, this is where you'd set which tool number it is. So if it's in tool position 5 in your tool changer, that's what you'd put in, and by default the length and diameter offsets match that. I advise you input as much data here as possible when you're setting the tool up, so that you know exactly which tool it is, and that information appears in your NC file but also on your setup sheets. You can define custom shafts, so if you've got the next tooling you can do that, and we can go and create holders as well and build up a library of those if we want. So we'll just grab a marry tool holder for now, and then you can put in your default feeds and speeds. Now typically you'd end up having to adjust these anyway per operation, so you just get some base safe feed rates in here. And then it's important that you define the number of flutes. So it's a pretty straightforward way of visual way of setting up your tools, build up your library, and then you're good to go. So the first thing we typically do here is face. So we'll use a 2D toolpath to do this. The first thing I need to do is pick my tool, and I'm going to select one of my existing tools from my document here, and I've got a 63 mil face mill. And I'm just going to click OK. So that has generated a valid toolpath very quickly, because in my setup I define what the stock is and I define what the model is, and the toolpath understands that. Even though it's a 2D toolpath, it understands that my bottom height is my model top and my top height is my stock top. So we've got this parametric relationship being set up between the CAM toolpaths and the model itself. Now, just to talk briefly through these tabs, the first one is always the tool and anything relating to the tool. The second one is always about the geometry that you want to cut, or the geometry you want to avoid. So in 3D toolpaths, that you have a whole bunch of extra options in here for confinement and touch avoid surfaces, and anything to do with the model or geometry. So typically containment in the X and Y plane when you're looking down onto your job. And then the third one is your heights. So containment when you're looking in elevation. So you only want to generate cutting toolpaths between an upper and lower Z height, but not above that or below that. Then you can controlling how the tool moves from one toolpath to the next, or from one pocket to the next. The next one's the passes tab, so anything to do with the actual cut itself. So all of the blue section of the toolpath, the amount of stock you want to leave, how many step downs you want to do, all of that is and the width of cut, depth of cut, all that sort of stuff. That's in the passes tab. And then the linking tab is about how the tool enters and exits the cut, but also links between one cut to the next within that toolpath. So now we've decked the top of our part, we can quickly rough out our part. And so here again, I want to change my tool, and I'm going to go to my new library and grab that tool that I created before. Select that. Now it's going to copy that from my library into my document. And I can just click OK on this and see what I get. So this is analyzing the full 3D model and removing all the material that's required. All right, so we can see that we're actually I planned out to have my stock removed down to this flange down here. So we just leave this top hat for the second operation. And at the moment it's kind of stopping short of our model. So what I need to do is edit this adaptive toolpath and change my height. So at the moment my bottom height is set to model bottom, but it's stopping short of that because I've got stock to leave on by default. So I'm leaving 0.5 mil on the floor. So that's why it's stopping 0.5 mil above the bottom of the model. What I want to do is use selection here and pick a bottom reference. I'm actually going to pick, they can't quite see it, but yeah, the top face of this flange here. So if you can't quite grab it because it's kind of hidden by this face on the side here, you hover your cursor roughly where you think it is, then right click and go to select other, and you can cycle through this list until you get to the face that you want. Select that. Now it's going to cut down to that face, but again it's going to stop 0.5 mils higher than that. So if I wanted to make sure it got down to the floor but still leave 0.5 mils everywhere else on the model, I should offset it by the same value. Now it's a good opportunity to show you the two different tooltips which are available in HSM. So all the way through the software you can see these tooltips which appear, which help explain what these functions are. But if you hold down Shift on your keyboard and hover over them, you get a different tooltip. And here we can see that the parameter name for this input is vertical stock to leave, and it's important you pay attention to the case of each letter. And so we can see that the first letter of each new word after the first one is uppercase. So vertical stock to leave. So if we come into here and we want to go down, so minus another amount, which is vertical stock to leave. And it goes black as soon as that's valid. And we can see that's 0.5. If we come back here and change our stock to leave to 1 mil, come back, we can see so we've created a parametric reference between the two, which is good practice to get in the habit of doing. And then if we click OK on that now, the toolpath will just go ahead and generate. So while that's generating, we can go ahead and create a 2D contour, and we might want to use the same tool and just cut all the way around the outside here, and probably want to go down again we've got a radius on our tool, right? So it's a bull nose. So again, we can use the same technique. If we edit this tool and have a look at this, we get a tooltip. Hover over, holding down Shift, go tool underscore corner radius, and we can use that. So if we go selected contours minus tool underscore corner radius minus 0.5, so it's going to go past an extra 0.5 mil. Then it doesn't matter what happens to our model. If the model changes, the tool's always going to come past by that amount. All right, so that covers. Whereas in the difference between 3D and 2D is here we didn't have to select any geometry, it just knew where the model was and it's figured everything out that we need. Whereas with a 2D toolpath, we've had to give it an input. And we've got this red arrow here. We need to pay attention to that because if that's on the inside, the toolpath is going to cut inside the model and cut away most of what we want. So we have to make sure we get that right. Just click it to reverse it. There we have it. All right, so where I showed you here just a single selection, we could actually go through and do a whole bunch of selections in one command. So selected our first profile here. Actually, I'm just going to turn off the visibility of this. Excuse me. This stock, get it out of the way. So now we can easily access all of the selections we need. All right. So now we want to add some additional contours. Now, when I pick this geometry, we can see now we've got an open contour instead of a closed one. And in some cases, when you select open geometry, it doesn't automatically find all of the edges. This is where you need to select the blue line a second time, and you'll see this little mini toolbar appear with these filters for closed contour and open contour. Now, I don't need to go through and select each individual edge here to add the additional edges to the contour. I can just go and pick the last one, and it will automatically find the other edges between the two. Make sure you hit apply to accept the contour, and we're good to go. If we wanted to cut just along this edge here, we select it once, select it a second time, switch to open, and then hit OK. All right. Remember, don't clear it. This kind of gives you a bit of a clue as to how to manage your selections as well, because if you click the red X on here, it's going to wipe out all of your selections. Whereas if you just want to get rid of one selection that was incorrect, you can select it again and click this dustbin, and it will just get rid of it. You can also use the control key on your keyboard to deselect stuff. So again, we'll come in here, pick out open contour, pick this edge. So we need to select that again. So click it a second time to activate the mini toolbar, pick the last edge in the chain, click apply, and we've got what we want. So click OK, and now we've got toolpaths at all the individual heights. Now, obviously, because we had this additional offset on the bottom here, this is a bad idea, but we'll just leave it for the sake of example, and you'll see the tool crashing in the simulation later. All right, where is my slide deck? Hole making. All right, so we'll just do some quick drilling here. So if we select drill, we'll pick a drill. So we've got this particular drill here, and you can either switch to the geometry tab and make the selections, or if you just pick the geometry, if it's valid geometry, it will automatically switch to the geometry tab for you. Now, I could go ahead and pick all these other holes, but because they're all the same diameter, I can turn that on and it's going to go and find them all. There's a whole heap of extra options in here for filtering automatic hole selection. So explore those, and there's lots of tutorials online about it. So that's now gone through and selected all of our holes, which is super handy. It's set the hole depth for us, because the bottom height and the top height is set to hole top, hole bottom. Now that is based on the top ring and the lower ring of the cylindrical face that you selected when you inputted the geometry on this tab here. So if we wanted to make sure that we were treating this conical face as part of the same hole selection, we can turn on auto merge hole segments, and you'll see this green line increase in height when I turn that on, because it's now effectively added this conical face as part of the hole segment. All right, so if we want to deal with these, we want to spot drill, we can either use the drill toolpath. So if we go and pick our spot drill, when we pick the conical face, it automatically sets the depth, but it's not always ideal on the tool. So you may want to actually machine these instead of just driving it straight down. You want to machine it after the hole's been drilled. So we can use 2D contour for that, and this is how you would apply chamfers or program chamfers to geometry that's already been modeled. Whereas here, if I wanted to deburr this edge, I wouldn't necessarily do that. So if we pick the bottom edge of all of these, we don't have select same diameter, and the order you select is important because it's the order it's going to machine them in. And we go to the passes tab. Now we've got this chamfer option which appear, which isn't there unless you have a spot drill, chamfer mill, center drill, or a ball mill selected. And now we don't want to add any additional chamfer width here because it's going to make the chamfer bigger, but we can add a tip offset in of, say, if we want 0.5. Now we're kind of limited here because we can't, the hole's quite small, so we can't go too deep. And we get our toolpath. All right. So when we simulate that, and we can just jump straight to that point by clicking on it, we can see that we've got a nice toolpath positioned just right. Okay. So we'll do some quick 3D surfacing here. Now, the ideal one to use in this scenario with fillets is flow, and it's a really easy one to demonstrate. But before I jump straight into that, I just want to show you the geometry tab here and the concept of containment. All right, so if we were to use a ball mill here, and just click OK. And while that's generating, well, it's already generated. So we can see that it's finding all of the vertical faces and surfacing them. Well, I only want it to work in this area here, so we can use a machining boundary based on a selection. Now, if we pick this profile here, that's not the boundary we want. So if you select it a second time, we can start growing the selection. You can see how by selecting this input, it's automatically found the rest of the loop. I click apply, and then tool center on boundary is fine. And if we click OK, it's now going to contain the 3D toolpath to just that area. All right. I actually want to use flow here, so I'm going to delete that. And we've got flow up in the corner here. And this one's slightly different because there's no containment boundary. It's totally driven off of the surfaces you select here. Now, it's important you get all the arrows pointing in the same direction. All right, we actually want it to flow along the surface like this and do maybe 5 passes. Click OK. And there we have it. All right, so really nice, clean toolpath. And when we simulate that and jump straight to here, we can see that the tool is stopping right on the point, on the contact point of that face. So we're kind of getting a really super efficient surfacing toolpath. All right, so for simulation, I'm just going to jump back in to the one I prepared earlier. So we've got our probing in here for setting our coordinate system, some manual NCs for if you want to leave yourself some notes, you can access that from in here. We're facing off the top of the job. We're roughing it out, removing all the material. I'm actually roughing this out independently. I wanted some slightly different settings for roughing out that fillet. I've used the bore toolpath, which is just a simple 2D toolpath, which results in a 3D output. It's just a simple face selection. So very similar to how I showed you to use the hole tool, the drill toolpath. I'm using 2D contour to finish around the outside. I'm doing some rest roughing in here, so I've used a smaller tool to get in closer to these corners, and it's a 3D toolpath, 3D adaptive, but I've just turned on rest machining here, and then it's comparing all of the material that's been removed in the previous toolpaths to what's there now and what it needs to remove, and then just puts toolpaths in into the areas that are needed to get rid of the remaining material. And then I'm just using 2D contour to finish off those walls, and 2D pocket to finish off the floor in here. Again, 2D. So I'm finishing the floor and the wall independently from one another in 2 separate toolpaths. Doing my drilling. I've actually used a pattern here. So the patterns are interesting. You can access that from up here on the ribbon, and anything contained inside the pattern folder gets patterned. All right. So here I've just patterned around the center axis, the 0 point, the XY0 in the Z orientation for this part, and rotated the toolpath around to the other side, and it works perfectly in that scenario. I just had some odd issues with the geometry on this side of the part, and I wasn't getting a nice flow toolpath as a result, so I just did a circular pattern to overcome it. And yep, so I'm doing my whole chamfer. I showed you how that's programmed, and then deburring. I will just cover this briefly because it's where this is a modeled edge. In here, on these edges, they're not modeled, so I need to specify what my chamfer width is. So this is going to put a 1/4 of a mil chamfer onto this hard modeled edge. So when we simulate that, just get to here. There we go. Now, once you're playing, if you pause, you can left click and drag on screen and just control the position of that tool with your mouse. So now I can left click and drag, pull this around, and as it comes around the corner here, just before it disappears around the back, we can see that we've got that 1/4 of a mil chamfer being applied. So left click and drag once you've got once you're actually playing the simulation, hit pause, left click and drag, and you can control the position of the toolpath at any position, as well as selecting these nodes like I've shown you a few times. All right, then I've just used a tap to do the threads inside those holes. Exactly the same toolpath as I showed you for drilling, it's just using a tap tool instead. Now, I can simulate individual toolpaths or groups of toolpaths by using Shift Select and Control Select, or I can simulate the entire job by selecting the setup folder. I'll turn my toolpaths off, turn my stock on. I can change the color of my stock to use material and hit play. So you can see that down here we've actually got this little collision. It's a false collision because the probe is going to collide with the stock. That's the whole point of it. But you can see the problem. You can also turn on stop on collision so that the simulation will actually stop at that point. We'll speed it up. We can just go full speed right the way through to the end. And you can also just skip ahead to individual operations. We can show transparent and part comparison, so we'll get to that in the end once we've turned that on, once we've got everything that we want. So rest roughing's happening at the moment, just moving that remaining material in the corners, ready for the finishing operations. Alright, so there's the surfacing happening. Right, we'll just skip right the way through to the end and turn on our show part comparison. And we can see that the red is gouging, the blue is material left on. Now this is showing up as a gouge because we don't have the chamfer modelled, we're knocking it off with the chamfer mill. Alright, so once we've got everything simulated, verified that it is what we want, we can post-process that out, choose our post, and generate our code. That will fire up HSM edit. We can view all of our G code in here. We can also use the backplot and just check the outputs, what we expect. There's a whole bunch of functionality in here that you can use if you want. It's actually a pretty cool little editor. You can set up your tool libraries in here as well and set up stock models and all sorts of stuff. But for a lot of people, this is really useful. You can set up DNC, and through a serial connection between your PC and your CNC machine drip feed code. So on older FANUC controls, which have got limited memory, then this is a really neat feature. In addition to being able to output your NC code, you can also output a setup sheet. There's a few different posts you can use. For that, the default one creates a HTML setup sheet, and it just lists out all of the tool definitions, like an overview of the job, number of operations, and estimated cycle time, the overview of the tools, and then an overview of each operation and which tools used when. And this is all completely customizable. You can also use an Excel setup sheet post as well, and you can find those in the installed post library. If you change the type in here to setup sheet, you'll see all of the different options available to you. And that's it. So hopefully if you haven't used HSM before in the collection, you can see that this it's pretty powerful for a lot of people and offers a lot of value. So if anyone's got any questions, just run over a bit on time, but I've got plenty of time. So if any of you have got any questions, just type them into the questions box, and I will get them answered for you. The questions don't have to be on what I've shown you today. It can be anything. If you've struggling with anything in the software, I can cover it for you. Okay, if you think of any questions afterwards, then my email address is scott.m@cadpro.co.nz. Feel free to email me or just call the office, and we can have a chat. Thanks, everyone. Have a good day.